Hello, welcome to 6.2, Differential Equations, Growth and Decay is what we're going to discuss here. Now, differential equations is actually a whole course. After Calculus 3, there's Math 285, which is differential equations. I encourage everyone to take it. You're going to learn a lot. You're going to just really feel like you're growing academically. Even if you don't need the class, take it. It gives you a much different perspective on the world. I mean, on rates of change and things like that. I remember when I was a student, I had taken differential equations and I went to visit a friend whose brother-in-law just dug a big well, and it was, I had a pump on there, and I was able to calculate the volume of the underground aquifer, how much water it held, knowing the pump rate when he was able to empty it and do that, but also to calculate on how the refresh rate is on the pump on the well underground. Really interesting things. So I just have to stress how much I didn't mean to hit the microphone. How much I learned and I was able to apply. Now, I pulled the screen down because we have that problem with the light right about here, but I'll put it up in a second. 6.2, differential equations, growth and decay, separations of variables. To solve a more general type of differential equation, we write the equation so that so that each variable occurs on only one side of the equation. So you want to separate them. You know the song by Offspring, keep them separated? Okay. I'll stop being corny. But here we are with example 1. If I can get the screen to go up. There we go. Solve the differential equation dy dx equals 4 minus x. So this is kind of the procedure for it. Some people would probably view this and say, well, that's not exactly, but this is the procedure, how we go about it. We have a dy dx equals 4 minus x. We say dy dx times dx equals 4 minus x dx. Not really that's what's happening, but we're moving that over. This goes away. And if we do the integral of dy, we get the integral of 4 minus x dx, meaning y equals, and this integral is 4x minus x squared over 2 plus c. And that's it. What I'm saying, this isn't exactly what happens. This is because this isn't a number here. The dx is not a number. It's telling us with respect to which variable are we integrating. But the idea is to separate them, and we have our dx's on the other side. So for example 2, the same thing holds. You're probably saying, but Jeff, it says y prime, not dy dx. Well, recall that y prime is dy dx. It's another way of writing it. So we could say dy dx equals 6x over y. Bring in the y over, multiply both sides by y and by dx. We have y dy equals 6x dx. So the integral of y dy is the integral of 6x dx. Y squared over 2 is equal to 3x squared plus some constant. If I subtract 2 from both sides, y squared equals 3x squared minus 2 plus c. I'm going to call this C1. No, I'm multiplying, I'm sorry. Multiplying both sides by 2. Got a little confused there. That's 6x squared minus 2 times c1. Now, that's 2 times some constant. Well, we don't know. Let's call it c2 then, or just c. So y squared equals 6x squared minus c. Some other constant, some other unnamed constant. And we get the actual constant after we plug in initial conditions if we had them. So y would be equal to plus or minus the square root of 6x squared minus c. If we would have brought this over, we would have had ourselves we could have brought it over in this case, had ourselves a hyperbola. Okay, growth and decay models. dy dt equals k times y. So notice that the derivative, this is the derivative, the rate of change is proportional to y itself, and k is a constant proportionality. So the rate of change is proportional to the original value of y. The bigger the y, the bigger the rate of change. And that's actually not true. If k was negative, the bigger the y, the smaller the rate of change. So it depends on what k is, positive or negative, if it's a growth or decay. So 6.1 theorem says exponential growth and decay. If y is a differentiable function of t such that y is greater than 0 and y prime is equal to ky for some constant k, then y equals c e to the kt is the solution of the differential equation. Big deal here, where c is the initial value of y and k is the proportionality constant. Exponential growth occurs when k is positive and decay occurs when k is negative. So example 3 says write and solve the differential equation that models the verbal statements. The rate of change of q with respect to t is inversely proportional to the cube of t. So dq dt is equal to k over t, k, Jeff, over t cubed. It's inversely proportional to the cube of t. So dq equals k over t cubed dt. The integral of dq does not stand for Dairy Queen, is equal to the integral of k, I'm going to call this k times t to the negative 3 dt. So that q equals t to the sorry, I forgot my k times t to the negative 2 over negative 2 plus some constant c. So the function q is k over negative 2t squared plus c. Let's go on to example 4. Find the function y equals f of t passing through the point 0, 10 with the given first derivative. Use a graphing utility to graph the solution. So dy dt equals 3/4 y. So if I divide both sides by y, I have 1 over y dy equals 3/4 dt. The integral of 1 over y dy equals the integral of 3/4 dt. So this is going to be the natural log of the absolute value of y equals 3/4 dt. 3/4 t plus some constant c1. Now you're probably saying, hey Jeff, you could use that shortcut formula. Yeah, this is how we get to it. So we could use it in the future. I wanted to do it this time. Now e to the natural log of the absolute value of y equals e to the 3/4 t plus c1. And e to the natural log of y, that's just going to be y. Y equals e to the 3/4 t e to the c1. And this c1, we're just going to call c. So y equals c e to the 3/4 t. And that's how we get to that one formula when you have the derivative is directly proportional to the original value y. Now it tells us passing through the point 0, 10. So that means 10 equals c e to the 3/4 times 0, where 10 equals c times 1. C must be 10. So y equals 10 e to the 3/4. Okay, that was fun. I'm going to go on now, on to example 5. Write and solve the differential equation that models the verbal statement. Evaluate the solution at the specified value of the independent variable. The rate of change of y is proportional to y, so that means dy dx. And I say dx because we have x in this case. is equal to k times y. When x is 0, y is 4, so that would be 0, 4 is a point. And when x is 3, y is 10. So 3, 10 is another point. So having this setup means that y equals c e to the kt. We don't know what k is. We don't know what c is. Those are unknowns. I should call this x. Okay, so plugging in the initial condition, 0, 4, that's our c. It means 4 equals c e to the 0. So c must be 4. So we have y equals 4 e to the k times x. How about the 3, 10? 10 for y equals 4e to the k times 3. 10 fourths is 5 halves equals e to the 3k. The natural log of 5 halves is natural log of e to the 3k. So natural log of 5 halves equals k. So y equals 4 times e to the natural log of 5 halves times x. I forgot my 3. No. Okay. I did forget a 3, because that's equal to 3k. There. So natural log of 5 halves equals over 3 equals k. Now we can put this back in. Y equals 4e to the 1/3 natural log of 5 halves times x. Now, we could take this a step further. This power, this coefficient can become a power for the natural log, so y equals 4e to the natural log of 5 halves to the 1/3 power times x. And you could leave it like this. You could leave it like this up here. Either one's fine. I'm going to suggest you consider this, be open to it. Don't feel like you have to do it, though. You could treat this as y equals 4e to the natural log of 5 halves. 5 halves being raised to the power of x over 3. Why x over 3? Because it was 1/3 x. You can make that x a power as well. What this has the benefit of doing is e and natural log cancel, and you have 4 times 5 halves to the x over 3. No more e's. It's kind of interesting. So in the last part it says find y when x is 6. Y would be equal to 4 times 5 halves to the 6 over 3. That's 4 times 5 halves squared, which is 4 times 25 fourths, which is 25. Okay. Let's go on then to example 6. I think I typed something wrong in the calculator when I did this by calculator before. Okay, going on to 6 then. Radioactive decay. Radioactive radium has a half-life of approximately 1,599 years. Wow. What percentage of a given amount remains after 200 years? So radioactive decay is going to have formula y equals c e to the kt. Now, the way this works, after 1,599 years, we have half what we started with. So c is what we started with. After the half-life period, we have half of that. So 1/2 of c equals c e to the k times 1,599. So 1/2 equals e, c is divided out, e to the k times 1,599. The natural log of 1/2 equals natural log of e to the k times 1,599. So natural log of 1/2 equals 1599k, and divide both sides by 1599. K equals the natural log of 1/2 over 1599. So our formula becomes y equals c e to the natural log of 1/2 times, that amount times 1 over 1599 times time. So y equals c e to the natural log of 1/2 raised to the power of t over 1599, because they become coefficients. That's a power of the term inside the natural log. So y would equal c times, and the e and the natural log cancel. That's 1/2 to the t over 1599. So there's our half-life formula. So how much remains after lost my train of thought, after 200 years? Y equals c times 1/2 to the 200 over 1599. Now the danger you have here is with the 1/2 is forgetting that this is 1/2 raised to the power. If you do 1 to that power over 2, you're going to have problems. So it's not a bad idea to change this to 2 to the negative 1. So it becomes c times 2 to the negative t over 1599. You can do that as well. Also make sure your power is in parentheses. So y equals c times 0.9169. So 92% of the original amount. We'll go on to example 7. It says find the principal P that must be invested at rate R, compounded monthly, so that $1 million will be available for retirement in T years. So R equals 6 and T equals 40. So the amount is equal to the principal times 1 plus R over N to the NT power. 1 million equals the principal P's we're trying to find times 1 plus 0.06 over its compounded monthly over 12 to the 12 times 40 power. So this works out to be 10.95745. We divide both sides by 10.95745. And P would be $91,262.11. Really didn't require calculus for that one. Okay, move on to example 8. Find the time necessary for $1,000 to double if it's invested at a rate of R, compounded annually, monthly, daily, and continuously. So our first case, $2,000 equals the $1,000 times 1 plus 0.06 over 1, annually is 1 times a year, to the power 1 times t. So we'll divide both sides by 1,000. 2 equals 1.06 to the t power. Natural log of 2 equals natural log of 0.06 to the t. So natural log of 2 equals t times natural log of 1.06. So t would be natural log of 2 over natural log of 1.06, which is 11.9 years. Okay, part B, again, $2,000 is what you get. Doubles $1,000 times 1.06, no, 1 plus 0.06 divided by 12 to the 12 times t power. So again, dividing by 1,000, 2 equals, and 1 plus 0.06 over 12 comes out to be 1.005 to the 12t power. Natural log of 2 is natural log of 1.005 12t, which means natural log of 2 equals 12t times natural log of 1.005, which means t equals natural log of 2 over 12 times natural log of 1.005, and that would give us 11.58 years. Now let's go to daily. 2,000 is 1,000 times 1 plus 0.06 over, should I do 365? Yeah. The banker rule said it'd be 360, but we'll go 365 just to not have to teach that concept. So 2 equals 1.000164 to the 365t. Natural log of 1.000164 to the 365t. So natural log of 2 equals 365t times natural log of 1.000164. We'll divide both sides by 365, natural log of 1.000164. And t equals, again, 11.58 years. Really not much benefit to going to daily in that case. And D, continuous. 2,000 equals 1,000 times e to the 0.06t. Dividing both sides by 1,000. 2 equals e to the 0.06t. Natural log of 2 equals natural log of e to the 0.06t. So the natural log of 2 equals 0.06t. T would be natural log of 2 over 0.06. And that comes out to be 11.55 years. Pause if you need to pause that. We're going to go on to our last page here. So the population in millions of Egypt in 2007 was 80.3. The growth rate expected to be continuous is expected to be continuous at an annual rate of k being 0.017. Find the exponential growth model for p equals c e to the kt for the population by letting t equal 0 in 2000. Use the model to predict the population of the country in 2015 and discuss the relationship between the sign of k and the change in population. Well, first of all, k is positive. What do you think that means about the population? So for A, we have P equals C e to the kt, and at time equals 7, we had a population equals 80.3 million. So 80.3 equals C e to the 0.017 times 7, because our k is 0.017. So 80.3 equals c times e to the 0.119. Divide both sides by e to the 0.119. C equals 71.3 million people. So P equals 71.3 times e to the 0.017 t. Now in part B they ask us to predict the population in 2015, so that's 15 years later. P of 15 is going to be 71.3 e to the 0.017 times 15. And that's going to be 92 million. So part C says, discuss the relationship. Well, K is positive and the population increased from 80.3 to 92 million. So a positive K means a positive growth rate. They're increasing in population. Okay. And one last example from this section, so pause it if you need to pause that. When an object is moved from a furnace and placed in an environment with a constant temperature of 80 degrees Fahrenheit, its core temperature is 15 degrees Fahrenheit. So at that instant, it's 15 degrees Fahrenheit. So the initial temperature is 1500 degrees, I should say, not 15. 1500 degrees Fahrenheit. 1 hour, not once hour, 1 hour after it's removed, its core temperature is 1120. So find the core temperature 5 hours after the object is removed from the furnace. We're going to use y prime is k times y minus t. And t is 80 in this case. T is the ambient temperature. So that means that our dy dt is going to be k times y minus t. Now, this whole term then has to be divided over to here because it contains the y. And we'd have dy y minus t dy equals k dx. The integral of y minus t dy equals the integral of k dx. This becomes y squared. No, I'm sorry, this is 1 over. That becomes the natural log of the absolute value of y minus t equals kx plus c. Call it C1. So e to the natural log of the absolute value of y minus t equals e to the kx plus c1. That cancels. Y minus t equals e to the kx, e to the c1. So y would equal e to the kx times c, so I'm just going to call this part c, plus t. So y equals c e to the kx plus t. Now our t is 80, so y equals c e to the kx plus 80. And we have the condition, this is after 1 hour, we're at 1120. And at 0 time, we're at 1500. So at 0 time, 1500 equals c times e to the 0 power plus 80. So 1420 equals c. Y equals 1420 e to the kx plus 80. What about that k? After an hour, it's 1120. So 1120 degrees equals 1420 degrees e to the k times 1 plus 80. Subtract 80 from both sides. That's going to be 1040 equals 1420 degrees e to the k. Divide both sides by 1420 degrees. And that reduces to be 52 over 71 equals e to the k. The natural log of 52 over 71 is natural log of e to the k. So that means we're going to have, I'm going to go with the decimal on this. K is approximately negative 0.3114. And our formula would be y equals 80 plus 1420 e to the negative 0.3114t. And the last question is, what is the temperature going to be after 5 hours? So y of 5 is 80 plus 1420 times e to the negative 0.3114 times 5. And that's going to be 379.3 degrees Fahrenheit. And that'll do it then for 6.2, differential equations, growth and decay. Hope you enjoyed that. Talk to you guys later. Send me your questions.